Hey guys, this is GKCS. We have Kirti Purswani, and today we are going to talk about GitHub code search. It's very useful if you are debugging something, you have a bug, you know the log line of the bug. All you have to do on GitHub is go type in that keyword and you get to see all string matches, and so you can find the log line where there was a mistake. I and Kirti have already written some stuff here so that you don't have to suffer our thought process while we write this down. Firstly, it's an exact search. So you don't have things like, if you're searching for mouse, then I will not search for mice. So, although these two are similar terms, GitHub doesn't care. It looks for the exact string match.
Also, it is not fuzzy search as well. It is not just similar words. It is also like if there's a spelling mistake also, like if it is instead of public, if you suppose write PBULIC, even then it is not going to search. It has to be exact search.
Yes. So if instead of writing public, if you write we miss the B, GitHub doesn't know. It will search for PULIC, not PUBLIC. Absolutely. Other types of searches which are more relevant is all org search, meaning all repositories in your organization. So for example, if you work at Facebook and you want to see only Facebook repositories being searched, and then you have a specific repository search. So maybe you are an engineer for a particular team, they have one repository that they work on, or you know the repository where the bug has occurred, you can do a search over there. So a single repository search is also possible. Kirti, have you ever used this functionality? I use it very often.
I also use it everyone uses. I think every time you have a bug or you have an issue and you want to search for it, I guess we all use it a lot.
Yeah. Okay, few more interesting things before we dive into the high level architecture. Number one, how many files are we talking about? Right? Just to get a rough estimate of what kind of search effort do we have to put in. So if you look at the total number of files, GitHub has roughly 500 million repositories. This is public information. You can read the GitHub blog, link in the description. 500 million repositories means if you assume 1,000 files each, that's 500 billion files. If you assume that each file is really large, which is 200 KB, that turns out to be 200 into 500 terabytes, which is roughly 100 petabytes. This is a bit of an overestimate, or it just looks like a really large number. The reality is you're going to be searching in a repository most of the time. So when you're searching in a repository, you have 200 KB into 1,000 files. That turns out to be 200 megabytes. And then Kirti suggested that we use an optimal order n algorithm, KMP, to search for a substring. 1 MB of data takes around 20 milliseconds. So 200 MB of data is going to take around 4 seconds.
The point of discussing this was just that searching, just storing the entire thing as it is and then searching will not be efficient. So that is why in this case, discussing how are we going to store the data is very, very important. And that's a very important aspect in HLD, right? So capacity estimation gives you an idea that what all things do you have to focus on.
Absolutely, yeah. Well, a brute force approach is going to get us nowhere. 4 seconds is not the kind of latency that people are looking for.
So maybe we can start from there, that how are we going to store the code, also like repository wise, or like, how are we going to store it? Because here we said that in a single repository it is 200 million MB of data, but then we know that some, like, they can be hotspots, right? That some will be huge repositories, some will be small repositories. So how are we going to store the code is probably somewhere we can start from.
Let's try a basic approach. Let's say, this is my desktop or laptop, and we write some code here. After writing the code, we commit and then we push changes. So pushing is going to send it to some server on GitHub. So let's say this is the GitHub file server because we are pushing changes. Okay. So we are transferring file data here. Now GitHub file server has to store this file somewhere. So that will be a file system. Let's note that down.
Also, when you're thinking about file system, in cases like this, I would suggest that we could also probably mention that we could use a file system like HDFS because we get to use the entire Hadoop ecosystem, and MapReduce and Spark, like these tech will really help us in this system, right? So this is a good use case for HDFS, yeah.
Yeah, because there's, like you said, there's going to be search involved, there's going to be some processing involved, and like D stands for distributed, so GitHub has 200 petabytes of data to store. There's no way a single file server can do that. So yeah, totally agreed, Kirti. This is a great idea. Okay, since we are talking about it, since we are talking about the distributed part of things, how do we distribute it in a way that is efficient for the GitHub file server? For this, what we need to do is look at how is data stored and how is data retrieved. Mainly how is data retrieved, because storage is rare, retrieval is often. So on GitHub, we are looking at the access patterns being, for search at least, it is get me all repositories in an organization, get me for a single repository, and get me all public repositories.
Do you want to talk about the API, like what all information we are going to assign and what is expected to come back?
Okay. Kirti, I see you have started this. Do you want to write that down? Yeah.
Yeah, sure. Well, okay, so we are doing get, basically search in our repo, right? Okay. And what all things are we going to pass inside this? We will be definitely passing the word that we are searching for.
Yes.
The repo, right? And obviously the API dev key, basically we'll have to see whether the user has
access on. Yeah.
Yes. So user ID also. Then what else?
I think, yeah, the repo, along with that, we also have searches which are sometimes org wide.
Right. So do we want two different APIs for that, or do we want one API where we mention that this like repository wide, or is this org wide?
I think we can use, maybe the repo can be an array, and so you have for the entire org, but then you will have to first search all the repos in that org. So and then whether you have permission or not. So instead, maybe you're right, org. Just mentioning org or repo, the type is better than sending it as an array.
Correct. So instead of repo ID, there would be something, basically some unique identifier, which is going to tell whether this is like a repo ID or an org ID, and that will be self-explanatory that, okay, this is a org ID or repo ID. Does that make sense?
Okay, so you're going to have this unique ID, and it's going to have something like org underscore, maybe the org ID is 123. Okay. Yeah, that makes sense. Stripe uses this. It's really helpful for debugging, guys, and it's really helpful for putting things together. So you don't have to add additional parameters. Or you can always add a complex object, but this is interesting. We also have public searches, and so like you mentioned, Kirti, maybe you can just say p underscore org underscore so on. Yeah.
Correct. So actually, essentially, we can focus on one API. I guess that is, like, if we just talk about how this is going to happen, that is good enough, right? Yep. Yes. And also, since this is a GET request, I think a very important point that we should be talking about is pagination and filtering, right? Because the response of this, firstly, can be huge. They can, like, if we are searching for a, say, common word like include, that is going to be there in all CPP files, right? So the result is going to be huge. So how do we return that is also something important. So here, suppose in the header, if we have to do pagination, we can also be sending like offset and page number. That is one thing that we can do for pagination. And then filtering, that like when I said word, so instead of sending it in payload, I could also send it like in the query itself, like question mark and search for this word. So just FYI that is how the API can look like, right?
Yeah, I think we should mention that. So we have this GET request, and there we have the response object. We should talk about that also, but you have already mentioned that whatever be the response, we need some sort of pagination and offset.
Right. So the response will obviously, in the payload, we'll have like body, like in that they will be there. And we'll also mention in the headers that what is the page number at the offset. So
Okay.
page number is the offset and the
Is offset.
size, the limit.
The size,
Yeah.
yeah. Okay, Kirti, there's another thing that, so when we are getting this, so what will the response object look like? Apart from this, what are the each response, what is each response going to look like? Like if you search for include, like you mentioned, we get the file name, we get the file number, the line number. I think they give you the column number also. And
Right. So file name and okay. So there's another thing that we should be discussing, like when we search, right? So do we get the entire file ka data? Like because when we search, if we see we see only 4-5 lines, right? Suppose
yeah,
in the same file, include is used say 10 times, right? So is that like one search? Like are we returning the entire file, or are we returning like 4-5 lines around that and then just searching for it? So even if it is like 10 times in a file, like is it going to be one response or is it going to be 10 responses?
let's see. What I'll do right now is I'll just go to a GitHub repo. And Kirti, that's a really interesting point. I guess a product manager will come up with an answer for this, that whether we want to see the text in the response itself, or is it okay for us to just get the location and then let's say it appears in 30 locations, we query those 30 locations separately in a separate API. I would personally choose to query it again. Yeah, I'm not sure about you. What would you prefer? Would you prefer to get them in a response or query them again?
Query again, you mean like within a file also when they are repeated once?
No, no. If they are repeated once in a file, yeah, I would like to query, because what happens with GitHub search is they give you some text before and after it.
Correct.
So,
So those are different responses. So when we say ki give me 10 search results,
yeah,
even if it is within a file, those that will be like 10 results, right?
yeah. If it is within the
So
file, then we'll query the file just once and get the entire file, and then we will just render the parts where
so
the word exists.
so
Yeah.
that rendering is happening on front end or on back end when we are
Yeah,
returning?
so let me take an example so that it's easier for me to understand. Let's say we are searching for video here. Now you see that this occurs in the same file multiple times and it shows 3 more matches are there. Okay, there's one more match in the same file and here it occurs twice. So what's happening is it's showing me text around the substring. So from line number 6. And I can go and see the file if I really want to.
So in this readme, like so the 5 to 7 and 47 to 50, are these two different responses or is this one response?
What I would do is first I would go and ask where do they exist, the video, and it would all be different responses. Yeah.
Right. Okay.
Yeah. All of them would be like, so video is the search string. It occurs in readme at line number 6 and at line number 48 and 49 and 50. So, and then, the character number would also be different. Column number would be something.
Correct, correct. Okay, so let me just write it down. So basically file name and then row number and column number, right? So basically within this file, what is the row number and what is the column number, both we'll be mentioning. And also data around that, like maybe 3 lines of data.
Yeah. If it was me, I would actually make another query for this. So you would tell me that line number 7 of contributing.md, character number, let's say 20, starts with video. So once I would get this information, I would go and query GitHub again, stating that, this is the line I want, please give it to me.
That is definitely one approach, but don't you think you are adding an additional network? Okay, there are obviously pros and cons. There's no right way to do it. But if I do it, because when I'm searching, I know that I anyway have to show that in response. Why not just do it? Like just avoid the additional network call.
Yeah, I would keep this file in CDN, so it would be pretty fast and access control would be there in the CDN. The reason I would do that is because I would separate out the concern of search from fetching a file. Otherwise, what I'll have to do is I'll have to join the things together on the server side and then return a response.
I agree with you. I'm just for the sake of discussion so that others can also think about it. Uh, I agree that anyway we'll have to join and send it. But even like after we get the file name, row, column, uh, okay, so okay, in the front end, if I think of it like this, that file names can come and row number, but that is still rendering, something like that. That is the user experience, is what you're talking about.
Yeah, yeah. So this rendering, if it is already done by the server, it will be easy for the front end, but it will put a lot of pressure on the server, is what I'm thinking. If there's a public, so if I'm searching for video, and I say that get rid of this, it's not a repo search anymore. It's like a public search. So there's 46.4 million files. And I don't know how these guys are going to do the join on the server side.
Right.
Yeah.
All right. Okay. So this does make sense. Ki, we'll have one API for this, and then after from this response, we're going to make another GET request, right? And inside this, we'll be basically doing fetch file, right? And here we'll be passing again the user ID and the basically the file name, the row number, and the column number. Correct? And this again we can pass as query parameters. Yeah, and it is going to go to a CDN.
Right. Okay. This looks good. This looks good. Like we said, when we are storing file in a GitHub server, okay, we have this GET request, and now we want to get all the row numbers and column numbers. So for a particular search string. So is it okay if I rename this Kirti to search string?
Sure. Yeah.
There's no way that we are going to wait for 4 seconds. So just storing it in a distributed file system won't be enough. We will have to do something else. So here we have one approach, which is basically doing some sort of pre-processing. When you're searching for, let's say, include, then if you have already processed the files in a way that include is easily searchable in the files, then it's really going to help. And I think, Kirti, you already mentioned this. Did you try?
Yeah.
So let's say that this is the search engine. Okay, first thing that the search engine needs is it needs to build some sort of a data structure like a trie on top of files. So it needs to be able to pull data from these file servers and create a trie. So how is that going to look like? Let's take an example. Let's say we have, yeah.
Okay. A couple of things to consider over here. So this trie is going to be per repository or per org?
Yeah, I think that's a very interesting question. I think if it is per repository, it can help us, and that's what we need. If we need it per org, then we can just aggregate all the search results from all the repositories that the org has and then return it. But if the org has a lot of repositories, that will be like, again, that will be intense. So maybe we can cache that result.
Okay. So for a single repository, we have discussed that, okay, there's 200 MB of data, but converting that to trie, I think we'll be able to convert that to a few KB, which we can easily store in a particular trie, right? So that does make sense.
Yeah, the good thing about the trie is that it doesn't store all the words. It just stores all unique sequences in the file. So let's take the example of include, so that it's easy to understand this. So when we are searching for include, we are going to search for I, and then we search for N. Meanwhile, if there is someone who's searching for, let's say, I equal to, so maybe this is a for loop, I equal to 0. Then there's going to be some path for that.
here.
While include is going to have in. Right, so and in this way we can have the try spread out. We have in, and then include goes in this direction, inc. If it goes all the way to lude, then we know that the word include exists. If it is ind and then you have ia, that is India, that will be a separate path in the try. So the search is really fast. For the number of letters that you have in your search word, let's say 5, you need just 5 hops in the tree to find out whether it exists or doesn't exist in a repository.
So this is order of length of your search string, basically. That is how the search is going to work.
Super fast. Yeah, you're right. Yeah.
Yeah. Another very important point, guys, like just how in try structure, like if you have studied in DSA, how it is stored that in every try node we have basically a boolean that is this the end of the word. Basically, is inc a word in itself or not? But here our try structure is going to be even more smart. In every node we are going to have that, okay, if this is ind or inc, where all does it exist, in which file, and what is the row number, what is the column number. So when we search and when we return the search, there itself we can have basically this in is present in this file name and in this row number, at this row number, at this column number. Does that make sense?
Yeah, totally. I'm just like noting it down so that what you mentioned is even more obvious. Let's say there is a code file and then you have this at line number 30 and 120 is the character is the column number, and then you have another code file which has this at a different location. That's what you mentioned, right, Kirti?
Yep.
Okay. So this is that's a really interesting point. You're no longer storing boolean as to whether characters end here or not, or a count also sometimes tells you that how many characters exist. Here you're storing locations because that is what the access is calling for.
Correct.
Okay, amazing. We have this try data structure which we are storing, I think, per repository because that is the bare minimum. We have queries sent to us as search in an entire repository or all repositories of an org or public. So I think bare minimum will be for an entire repository, you have one try.
Correct.
Okay, let's note that down. If we have it for an entire organization which might have hundreds of repositories, we can
do the search parallelly 100 times, I think.
Yeah, that would work. So a parallel search would work, and if it's expensive, we can cache it also, because building the try is not going to be very. It's going to consume memory. So if we want, we can aggregate all the tries also of all the repositories and keep it for every org.
We can actually, because you're talking about cache, we could also cache like commonly searched words ka results, like for example error, debug, like so we could LRU cache is a good, again this is a very good use case for LRU cache. It's a good fit over here, right? Anything that is used a lot, that is searched a lot.
Yeah, because when you're debugging, let's say you debug for a while and then you're gone, you're never coming back. So if you're recently being used, you're in, otherwise you're gone. There's no frequency. So that's a good point. Okay, we have this search engine which is using tries. The question now becomes, how does it fetch data from HDFS? I think this will be happening, like you mentioned, HDFS has the Hadoop ecosystem with it. So some sort of MapReduce.
Do you want to quickly explain what is MapReduce for like beginners?
Yeah, I'm wondering whether we need MapReduce or just, it can fetch a file and create the try. MapReduce is a generic, powerful design pattern when it comes to data analytics, which helps take large amounts of data and process them. For example, if you want to find nearby restaurants to recommend, you can use a MapReduce design pattern. But in this case, I think
we have already pre-processed it, so we might not need it. But if we wouldn't have done the pre-processing, then it would have been a good fit, I guess.
Yeah. So, okay, here's the interesting thing. Like Kirti, you just brought up a very interesting point. We can do this in batch, or if when a person uploads a file to GitHub file server, maybe they can send an event to the search engine saying that this is the new file. Please go ahead and add it. So that would work. So maybe a
Yes.
message queue itself would work. Yeah.
Yeah.
Okay. And meanwhile, this is storage. If they want this. Okay, so we will probably go for this path, not map reduce. Now we have the search part sorted. Is there something that we are missing?
Okay. To just revise it quickly, could you just tell that, okay, this is how the GET request is going from here to here, exactly what is happening? Because it is happening in two requests, right? So I guess for further clarity, it will help. Yeah.
Okay, right, let's summarize. We have a code search being done by a person, a developer maybe. It goes to the GitHub file server. Here, the files are sharded according to repository or organization. I think organization is a better idea. We can have all the organization files in one place. At the same time, the file is added in a message queue, which sends it to a search engine. The search engine can maybe, you just get an event here, and then you can pull the file from the HDFS. Then what happens is this new file adds new nodes to the try. Okay, maybe new places where INC exist. If you make changes to the file, so let's say the file data is updated, the same thing is done. A new event goes, the search engine fetches that event, and okay, that's complex. Yeah. If you have updates, can this try work? You will have some deletions and some additions.
Some deletions and additions. So basically, in that node only, like how you have stored, right, code.py and code1.py, like over there itself, you could just basically remove and add. So yes, the if we have to talk about how complex that will be, it will basically order of deletions plus order of insertions, basically.
Yeah, maybe in this try, we can search for all the places where this file exists. We delete all those places, and then we
Don't you
rerun.
think that would be actually more expensive than the number? That depends actually on the use case, because if num like how many times, like you'd have to go through the entire try, right, in that case, to see where all does code.py occur, and then we'll have to see is there a change in this line or not.
That's true. We'll have to go through the entire try, and then find we have to delete this. That's true, and we'll have to do it for the org try also if we have aggregated. Um, that can be a problem. Meanwhile, and when we have to process that file, that updated file, newly updated file, and go through the try again and add the nodes. I think adding or processing the file is easy. Deletion is pretty expensive. Deletion requires us to go through everything.
Correct.
Yeah, I don't know whether we should keep a data structure which is just storing all the positions where this file occurs in this try. Maybe that's a bit extreme. Maybe not.
I mean,
Yeah, updations and deletions
it
happen
is.
reasonably often. So it's not something that we can ignore. What would you prefer, Kirti?
Actually, if I think about it, it is an expensive operation, right? Because if there are like 4 words in a particular line, if I just change one comment itself, you're basically changing 8 places in a try. That's a lot.
No, but we can't avoid that because we have characters. I mean, the column number, the row number, everything has changed. So I think
Right.
an easy way to process is just to clean out that file in your repo, and then you take one step up.
But the good thing is that, this can happen asynchronously, updating can happen asynchronously, but because search is a very common operation, it does make sense that we store and we optimize for that, because the updates, all the updates, like we can do it, we can probably use Kafka and we can have parallelism over there, and we can have basically, we can do updates like asynchronously, right? but it does make sense to optimize for search.
Yeah. So maybe for optimization, we can have a mapping of where does this file occur in this trie, because one file can occur only in one repo. The file is a collection of repos, so it can occur only in one trie. So noting down all positions where the file occurs is maybe a easy way for us to go and delete these entries and then just to reprocess the file. So that would also work.
Right. Also, we could use like a key value store which like Redis, which has like basically caching also, right? Which would actually make things very fast for us. Because max how big, like the length of the trie is not going to be that huge. So storing it in a map doesn't make sense. Like it will optimize things for us.
Yeah, we can just read the trie into memory, and then it's going to be like, I think, an MB at most. So cool.
That is also a lot. I think KBs is enough. Yeah.
Yeah, and yeah, but we'll have to build that structure and then search through it. So that will take order n. Okay, great. We have a way for additions, deletions, updations, all of that being rendered in search very quickly. Eventually, consistent system works here. We don't need to be like millisecond response time. We can show older entries, even if they're a few seconds old. Nobody's going to update the file and immediately search for it. So that's good. Finally, we talked about this part of the get request is done. We are looking at our second get request now, which is fetching a file. So when we are fetching a file, we are fetching it from CDN. We are mentioning the row number, the column number, and the file ID. And so we expect the CDN to say, okay, the previous 5 lines from this row number and the next 5 lines from this row number is what I'll give you. So you can render that code snippet.
Yeah.
Okay. Is there anything we should do here to optimize? I mean, does it help to optimize? Should we chunk the file so that the row numbers, you fetch only those row numbers that you care about? Or is this network latency much larger than whatever the file size can be?
I mean, it really depends on the use cases. We could have something like if we chunk huge files, like if the file becomes greater than this size, we could chunk it.
Yeah, that's I think that's a great approach. Yeah. So you have a bit of a hybrid approach where we look at a threshold file size, and if file is small, get full file, else send chunk. So because we are giving them the row number, the CDN is smart enough to say that, all right, do I need to chunk the file and send you just a part of it, or do I send you the entire file?
Yeah.
Okay. And the UI then has to render. So it gets the file and it renders on the client. Okay, I think this is it. Do we have any other part to this? We are able to store files, update them, search, and then also retrieve the locations.
Yep.
I think this does look good. Yeah.
Okay. By the way, let's just have a look whether this is what really happens. Okay, the moment of truth. Let's search for stuff here. Wait, we have network. Let's clear the network. Let's search for video. Okay, so we got suggestions. Again, I'm just clearing this out. This seems to be the query. Yeah. What is this? Responses here.
It's the entire HTML response. Okay.
Oh, okay. It's an entire. Oh, okay. And they're giving all of this stuff.
Yep. So it's one instead of us like how we did 2 queries. Basically, it is I guess 1 query, right? Instead of 2 API, it's 1 API.
Yeah.
Okay. Can you show the request also, like the headers and everything? How is it going?
Sure. This is the request. We did a search ? repo, and then the org. I think this is the
So
org.
it is the query parameter, just like we were talking about.
Yeah. And then
Type
equal to
the
code,
video. Yeah. And type equal to code. Yes, you're right. Okay, there might be other types. Interesting. And then you have this as the preview. So the response is HTML response. Oh, okay. And they have built the whole response and given it back to the UI So it just renders it. It doesn't even need to.
Yeah.
That's yeah. Okay. So in the same thing, you just get everything.
So how Gaurav keeps optimizing for the server, no, that we should not load the server a lot. See, server can do more.
Yeah, really. I thought that they'll make it. Oh, look at this. In fact,
Yeah.
it's very obvious here.
Yep.
They have even given the dot dot dot.
So
Yeah,
front end has to do nothing. Yeah.
exactly. And they've given the starting line number, ending line number, jump to line number, and they have given the position also, I think, and the end also.
That's a lot of network call, like so much of data
Yeah.
being
How
sent on.
big is this? How big is it? Timing? Waiting for server response, it took 580 milliseconds. That's not much compared to what it could have been. Because we waited for this, and my network also comes in. Like, it's not just GitHub which took 580 milliseconds. My
Right.
Airtel also took some time. So, yeah. Cool. So, in reality, it's much simpler than what we thought also. It's actually, this network call doesn't even exist.
Yeah, the second one.
We had actually discussed the pros and cons about having a second call and having one. So basically, there is no right and wrong. That is how GitHub does. I am sure that they must have thought through more. But then this is also not wrong. This is also like a good design, I would say.
We picked up a relatively simple use case, GitHub search. And even for that, you have to consider how to store files, how to update files, how to update your search data structures, what data structures should we use, where do we store the locations where a substring occurs, and what kind of APIs we need to design. So,
Right.
really interesting engineering that we are looking at. Thanks, Kirti, for picking this, and thanks for making this possible.
Thank you so much for having me. It is always a pleasure. And this is a series, guys. By the way, the next video will be on the other channel. So make sure you check out the description, and all the details are over there. And see you next time. Let us know what other topic you want us to pick.
Sure. See you. Bye bye.